Welcome to The Explainer, where we break down big ideas. Today, we're going to pull back the curtain on an incredibly elegant algorithm that's working behind the scenes in everything from your GPS to the enemies in your favorite video games. We're talking about the A-star search algorithm.
So, have you ever been playing a game and wondered, how does that character navigate this super complex maze without a hitch? Or how does your GPS app figure out the absolute fastest route in like 2 seconds flat? They always seem to know the perfect way to go.
Well, the core challenge is pretty universal. It's all about finding the most efficient path from some point A to a point B through a whole mess of possibilities. Whether you're looking at roads between cities or pathways in a game world, the trick is to find that optimal route without having to check every single option. Because let's be real, that would take forever.
All right, so here's how we're going to break down A-star. We'll start with its secret formula. Then we'll get into the art of the guess, which is really what makes it so clever. After we see how it finds the best path, we'll look at just how efficient it is. And finally, we'll talk about the price it pays for being so perfect.
Okay, let's dive right into the heart of A-star. What you'll find there is a surprisingly simple but incredibly powerful formula that guides every single decision it makes. This right here, this is the whole engine that drives A-star's intelligence. It makes A-star what's called a best first search algorithm. And what that means is, it's always exploring the path that looks the most promising at any given moment. And it does that by balancing what it knows for sure with what it can make a really good guess about. So the first piece of the puzzle, G of n, that's the easy part. It's just the cost of the ground you've already covered. This is the hard data. Think of it as the miles you've already driven or the number of steps your game character has already taken. It's a fact. It's what's in the rearview mirror. Now the second part, H of n. This is the secret sauce. This is the heuristic. It's basically an educated guess, a forecast of the journey that's still ahead. For your GPS, this is like the straight line distance to your destination, as the crow flies. It's just an estimate, but as you'll see, it's a really useful one. So you put it all together, A-star takes the known past cost, that's G of n, adds it to the estimated future cost, H of n, and gets this total estimated cost, F of n. And at every single fork in the road, it just chooses to explore the path that has the lowest F of n value. It's constantly betting on the route that looks like the best bet.
But here's the thing. This whole beautiful system, it lives or dies by the quality of that guess. That heuristic function, H of n, is what makes A-star so incredibly efficient. And as we're about to see, not all guesses are created equal.
To really get a feel for this, let's look at a classic AI problem, the 8 puzzle. The goal is super simple. Just slide the numbered tiles around until they're all in order. Here, the path is the sequence of moves you make, and we want to find the shortest one possible.
Now we can use different heuristics to guess how far we are from the solution. A really simple one, let's call it H1, is just counting the number of tiles that are in the wrong spot. But a much smarter guess, H2, is something called the Manhattan distance. This one adds up the total number of squares, up, down, left, right, that each tile needs to move to get home. It's a way more informed guess because it doesn't just know if a tile is wrong, it knows how wrong it is. And this brings us to a super important rule, the key to A-star's magic. The heuristic has to be what we call admissible, and all that means is that your guess has to be optimistic. It can, and often does, underestimate the real cost, but it is never ever allowed to overestimate it. It's optimistic, but it's not delusional. And by the way, both of our 8 puzzle guesses are admissible. And here it is. This is the big kahuna, the payoff for following that one simple rule. If your heuristic is admissible, if it never overestimates the actual cost, then A-star comes with an amazing guarantee. It will find the absolute shortest, most optimal path every single time. Not just a good path, the very best one. So how does that even work? How does an optimistic guess guarantee a perfect result? Well, it really helps to actually visualize how A-star searches for that path. This picture just says it all, doesn't it? A simpler, less intelligent algorithm might just search blindly outwards in perfect circles. But look at A-star. Its search is being pulled, almost like by a magnet, straight towards the goal. That's the heuristic at work, stretching the search in the most promising direction. Think of it this way. An algorithm like Dijkstra's is like meticulously searching a city block by block, exploring every single street equally. It's thorough for sure, but it's not very efficient. But A-star is like having a magic compass that always points in the general direction of your destination. It's just as thorough in the end, but it saves a massive amount of work by not even bothering with paths that are clearly going the wrong way.
And that focused search doesn't just look smarter on a diagram. The numbers back it up big time. It proves that A* is dramatically more efficient. And the better your guess, the bigger the payoff.
Let's go back to our 8 puzzle and look at the hard data. What you really want to pay attention to here is the nodes generated column. That's basically a count of how much work each algorithm had to do. A basic breadth-first search, or BFS, which is kind of like that search in circles method, explores a massive number of possibilities.
But now look at A* with our smarter guess, the Manhattan heuristic, H2. At a depth of 24 moves, it only has to explore a little over 5,000 nodes. The brute force method? Almost 300,000. Do the math. That's over 50 times more efficient. It finds the exact same perfect solution, but with a tiny, tiny fraction of the effort. It's the definition of working smarter, not harder.
Okay, so it sounds perfect, right? Guaranteed best path, super efficient, but there's always a but, isn't there? This guarantee of finding the perfect path, well, it comes at a price. A*'s power is incredible, but it does have one key limitation, especially when you start dealing with really big maps.
And that price, the biggest challenge by far, is memory. Think about it. To be absolutely sure which path is the best one, A* has to keep every single potential path it's ever considered in its memory. And if you're dealing with a huge space, like a map the size of a whole country, keeping track of all of those nodes can eat up a gigantic amount of RAM.
So of course, some very smart people came up with a solution. There's a really clever variation called IDA*, which stands for Iterative Deepening A*. And instead of remembering every path all at once, it just does a series of searches, and each time it allows itself to go just a little bit deeper. It basically combines the smarts of A* with a much more memory-friendly strategy, which is what makes it practical for things like really complex video games.
So when you boil it all down, A* gives us this incredibly powerful framework for solving problems. And its core idea is actually really simple. Just balance what you know for sure from the past with an optimistic guess about the future. Which kind of leaves you with a final thought, right? Where else, in science, in logistics, maybe even in our own lives, where else could that elegant logic help us find the best path forward?